Hello, my name is Brändli and I'm CEO of Sony Advanced Visual Sensing. Today I'd like to show you some of our most recent activities as well as some insights that we have gathered over 10 years of event-based vision sensors and algorithms. So I guess you probably have already heard of Sony. We've been doing technology for actually quite some time and quite frankly, we started already before Elon Musk or Steve Jobs were even born. Since we've been doing technology for so long, Sony's offering a wide range of products and services. You may know PlayStation, Sony Music, Sony Pictures, or our excellent TVs, cameras, or headphones. But what is lesser known is that we are also active in CMOS image sensors. We're not just active. I'm actually very proud to say that Sony Semiconductor is the worldwide #1 in image sensor sales, and we have the most advanced process for image sensors. It's actually very likely that you own one of our sensors. To always deliver the best and latest technologies in the field of image sensors, Sony Semiconductors has a series of research centers across the world. Sony Advanced Visual Sensing is one of them, and one of our main focus at the moment is event-based vision sensors and algorithms. The reason Sony AVS is focused on event-based vision sensors is because we've been doing so for quite some time. The majority of our team has been working in this startup in Cygnus, where we developed our own event-based vision sensing solutions from the sensor all the way up to the algorithms. Now what you can see here is that we have first worked in the field of drones, where we used event-based vision sensors for collision avoidance, and we've beaten state of the art when it comes to collision avoidance in dynamic environments. And then later on, we realized that we should better focus on applications such as inside-out tracking here and now in the context of virtual reality or augmented reality. Okay. Enough PR. Let's talk about technology. I stopped with telling how cool Sony is, and I'd like to use the opportunity that I get to present here at CVPR to share some of the insights and learnings that we made over the last few years. For a long time, I had this wish that we can somehow come up with a theoretical background that allows us to combine the world of transistors and devices and physics with the world of theory and algorithms and applications. And while we're not yet fully there, I think the following will give you some insights into what we have learned along the way, and hopefully we get some time that we can write up some of our latest understanding in what are good ways to characterize, for instance, signal to noise or dynamic range in event-based vision sensors. But for now, I only have a bit of kind of fluffy insights, but hopefully more to follow soon. So let's start off with the most basic question. What is a temporal contrast event? You may think this is a trivial equation or a trivial definition, but let's go through it. Now, as everybody, we define an event as the tuple of an address and a timestamp, and more specifically also a polarity. Now, what is very important in this formula is that this event is only created when the integral since the last event of the temporal contrast and the noise is above or below a certain threshold. Now, the dimension that is not necessarily trivial is the dimension that we have to factor in the noise. And what makes things a bit tricky is that the noise doesn't just distort the signal in terms of how much temporal contrast you actually capture. So in a single event does, even with the same threshold, not only capture a varying amount of temporal contrast, the noise also affects the integration time of that. So whenever you speak of noise, you cannot distinguish whether it's noise in what we call event magnitude so how much temporal contrast is actually encoded in an event, or noise in terms of timing accuracy when this threshold crossing actually occurred. And so not having the possibility to discern between temporal noise and amount of noise, amount of change that has been captured, makes it relatively tricky to come up with signal to noise definitions and other noise formulations. Now, when we look at the signal side of things, let's have a look at what an event actually is encoding. It's encoding the integral over temporal contrast. Now, this is according to the original paper by Lichtsteiner, and what you can see here is that the signal captured is the rate of change, so the rate of illumination change, normalized by the absolute illumination, which is equivalent to the rate of log illumination change. Now, this makes it relatively tricky to define signal to noise, because while a conventional image sensor has a constant input when a constant light is applied, an event-based image sensor has a constant input when a constant rate is applied. Now, this ties back into the previous statement, which is that if you are interested in figuring out what noise actually means and a constant rate is your input, then the variations in how this rate is encoded actually reflect your noise. Now, this is me pointing to the fact that currently many event-based image sensors are characterized looking at step responses which don't capture the temporal dimension, and depending on the circumstances, yield very favorable numbers despite the sensor being not so good in capturing the underlying rate. So an event encodes an integral of temporal contrast. So the event magnitude is a temporal contrast step. And we can either express this as a delta in log intensity, which makes it a bit hard unit-wise, or you look at it as an increase either in percent or as a factor. Now, usually we used to use percent. So we said if the light gets brighter by a certain amount, we said this is an on event of, let's say, 25%. Now, what makes this a bit odd is that when you have an on event of 25%, you need to have an off event of 20% to get back to the same level. So you have an increase of plus 25, and then you have a decrease of 20, such that you get back to the same level. Now, what is very interesting is when you start looking at factors, and which are, instead of kind of being used in a multiplicative fashion and then just added, but just multiplied, so let's say in that case a factor of 1.25, you can use it either by multiplying by 1.25 or by dividing by 1.25, and so you have a symmetric factor. That seems to be also a bit easier when it comes to expressing events in a mathematical terms. You can look at on and off events as just either using a multiplication or a division. Now, once we kind of captured what an event is, it's a temporal contrast step, we can look into what makes up a temporal contrast step. So what are contributors that contribute to this change in illumination? Now, once we did this, once we kind of tried to figure out what are the different components, what we realized is that there's following. There's a change in illumination. I'd say that's the most obvious one we notice from flicker events. But what is important here is that it's a change in log illumination. So that makes it usually a bit tricky, because when we look at light intensity modulations, it's usually in linear domain. Then there's a term that I have not seen so often observed in academic literature, which is a change in reflectance. Now, what is very interesting is that the event magnitude is proportional to the reflectance. So it's independent of the lighting, but proportional to the reflectance. Now that comes in very handy in passive computer vision. So when you then look at the last term especially, what you see is that the event magnitude depends on the gradient in the reflectance and the speed by which this gradient moves through the scene. So looking at this equation also tells you a bit more. A single event is in most cases not sufficient to do a lot. First off, it has a substantial amount of noise in there, and secondly, even the signal itself consists of modulation in intensity, modulation in reflectance, and then the visual flow expressed in terms of reflectance. So usually what you have to do is you have to take a set of events and make an inference on either one or multiple of these components. Now this is where a lot of the more recent work in the field of, for instance, contrast maximization come in very handy, because they allow you to correlate in space and time such that you can make an inference on the last few terms in here, and once you start just correlating in time, you can make an inference on the first two terms. Now again, I haven't seen yet that much research in the field of reflectance changes. So what is very interesting with this formula is that once you studied what makes up this temporal contrast and what are the main contributors to this temporal contrast steps, you can already kind of make an inference on what you can do with these events. Now, we tried to classify this here a bit. On one hand, you can use the events themselves as what I call entropy cues. Just the fact that there is temporal contrast is a good indicator there is something interesting happening. Now, this comes in very handy because in many applications, event-based vision sensors can run in always-on operation and can then be used as either smart triggers to wake up other sensing modalities or smart triggers to wake up downstream processing. So this is just using the raw event as a cue for computation or sensing. Now, once you start correlating the event-based data stream in time, either self-correlate or correlate especially against an active light source, you can then get out from this event stream a common signal. And so this is usually used in active lighting settings such as structures light or visible light communication, where you then can also use this correlation with this external light source to filter out, for instance, motion that is coming from the two terms or the three terms on the right, which are just kind of reflectance dependent. Then I would say the most common class of event-based vision applications either correlate in time and then try to find a flow direction that best explains the event stream, such that you can then, for instance, with contrast maximization, you can then assume that a given distribution of reflectance has caused this event stream. Or you can also do the other way. You can make an inference across the temporal contrasts to then figure out, okay, how must things have moved? So especially when you already have, for instance, a picture, you can get the derivatives on the picture and then just infer how things moved. So you can either kind of reconstruct the image, or you can know the image already and then kind of make an inference on the underlying motion. Now, I'd love to go a bit more into details how we at Sony AVS took all of these learnings to get to the point where we now can take the circuits and then our understanding of the circuits in such a way that we can characterize them such that the quality of the events that we get is actually meaningful for the applications that we use. And I hope we can eventually also publish some of these characterization procedures, because they try really to kind of connect these two worlds that we have been now working on for so long. But at the moment, I hope these kind of formulas and especially this the sort of learnings that I try to share give you a kind of a pointer to where we see some of the challenges. It's around how can you attribute for the right kind of noise in the right setting. So when you want to make, for instance, here in such a case, when you want to make an inference of the underlying motion in a scene, and let's say you already know the reflectance distribution, then you need to know how many events you have to integrate to reliably get to a motion estimate. Now, that strongly depends on how much noise there is in the circuitry itself, as well as how much other terms are contributing to the event stream. So that varies when you have a lot of flickering. You have to integrate more events, not just in total, but also for a given feature, for instance. And then at the same time, you have to make sure that you always integrate enough information given the quality of events that you have. Now, after all this theory and talk, let's have a look at a few examples of how we use these formulas at Sony AVS. Now, in a first application, I'd like to show you how we can use a set of events to make some inference of what active light sources could have triggered these events and how this can then be used to triangulate depth. In this video, what you see is how we have combined an active light source and an event-based vision sensor to capture 3D information. Now, what makes this very interesting is that the high temporal resolution of the event-based image sensor allows us not only to capture very accurate depth information, but we can do so also very fast. Now, another very powerful and widespread application of event-based vision sensors is using a stream of events to make some inference on how things in the scene have moved, so tracking. So we have developed our own tracking algorithms, and here the focus is mostly on making the tracking algorithm more robust, such that it can actually be used in applications. Now what you can see here is one of many event-based tracking dot examples, but what I find impressive is that even under harsh conditions, the dot tracking works reliable. So first off, what you can see is it's tracking the rotation of this disk with two dots on it very nicely in between actual grayscale images, but also when the conditions are more challenging, such when, for instance, the camera is actually moved. Now, I understand that many have been working on this topic before, but I think there's always like a good amount of engineering that then also has to go into making these solutions more robust. And so I think that's some of the activities that were really good at Sony AVS. Now, one way to tell that our tracking seems to be really robust is that if we compare it against OpenCV, for instance, here, and some fast motion, it turns out that we can track scenes that are not to be tracked with OpenCV. Now, this also applies to repetitive structures, which tend to be hard for tracking algorithms that need similarity metrics and can be solved with event-based vision sensors due to their high temporal resolution. Now, apart from tracking, event-based vision sensors can also be used to make an inference on the structure of the underlying world. In this application, we do so in a sensor fusion type of approach. What we were doing is we are combining the slow and power-hungry reading from a depth sensor with the fast and low power readings from an event-based vision sensor to get the best of both worlds. So depth readings with a high temporal resolution and without the need to send out enormous amounts of light into the scene to capture further footage. Now what you can see here is on the left the event stream, in the middle the original depth stream, and then on the right how we can combine these two data streams and infer the depth distribution in the scene based on this data. Now this is one of several activities where we try to use the events to their advantage, but still use other sensing modalities to complement the capabilities that we can do with events alone. Now, if you think that was interesting, and if you are interested in working with event-based vision sensors, we will continue to grow our team. And if you want to work with the world champion in image sensors on this super exciting new technology, I will be more than happy to see you in an interview very soon. So please look at our LinkedIn page, make sure that you follow us there, and then also from time to time and check out whether Sony has new positions open. There are also other really exciting research groups within Sony working on this and other new technologies in the field of computer vision and AI. So please look into these links, and if you have any questions, don't hesitate to reach out to me. We're very, very interested in getting feedback, getting questions, and understanding what makes you excited about event-based vision sensors. Thank you very much for your attention.